Raman is a vibrational spectroscopy which is capable of providing chemical and component information with high spatial resolution. The source is a beam of photons with wavelengths in the visible spectra from a pulsed laser. There are then lenses to focus light onto the sample and to collect the scattered light, and filters to purify the reflected light and scattered light so that only Raman light is collected. Photons are inelastically scattered by molecules within the sample and give up energy corresponding to vibrational levels within the scattered molecule. This lost energy is designated as Stokes. Energy gained is anti-Stokes, but is less intense. Therefore, Stokes energy is used. Scattered photons are detected and analyzed by a very sensitive spectrometer, yielding a spectrum showing energy losses which are characteristic of the molecule with which the photon interacts. There is a computer that 1. Controls the whole system and 2. Displays the spectrum and enables analysis of information. Molecules have characteristic phonon modes which can be found in literature and also match to resulting spectra. Generally, the interaction volume is the width of the laser on a photon size scale times the depth or penetration of the sample, which is based on the crossing angle. For example, a beam with a focal length of 20 millimeters and a crossing angle of 1.3 degrees. The interaction volume is a narrow and long volume of intense illumination in which the CARS signal is generated. The minimum sample size for a solid sample is 0.1 grams and 0.5 microliters for a liquid sample. It is important to consider sample stability and flatness, otherwise it will be difficult to focus the light. One major advantage of Raman spectroscopy is that virtually no sample preparation is required. This is because the technique measures how light is scattered off a sample rather than absorbed. Raman spectroscopy is applicable for non-destructive chemical and microscopic imaging of samples of all phases. It is well established and effective in various fields such as pharmaceuticals and cosmetics to determine concentrations and distributions of numerous mixed compounds. Raman is as well useful for geological and mineral identification, carbon materials, semiconductor lattice structure and defect analysis, and life sciences imaging of DNA, RNA, and single cells. Due to the weakness of the Raman effect, there are several limitations to the technique. Overall, the technique requires sensitive and highly optimized instrumentation. Long acquisition times and often sophisticated data analysis is necessary. The primary limitation is the presence of fluorescence in certain samples, like proteins and minerals. Fluorescence is a similar process to Raman, though it requires an absorption and emittance step, rather than just the single step for Raman, and it occurs in similar experimental laser wavelengths. Fluorescence is often more intense than the Raman effect, masking desired features. Some techniques exist for reducing fluorescence, such as using near-infrared lasers. Fluorescence is much rarer in this range, but this also significantly decreases Raman signal strength as it is proportional to 1 over the wavelength cubed, requiring much longer scan times. Raman signals can also be shifted by a range of experimental conditions including sample stress, changes in temperature, impurities, non-stoichiometries in the material, and the laser power. Increase in temperature causes wave numbers to decrease, while increases in grain size can have the opposite effect. The relationship to laser power is inconsistent, with increases in laser power initially causing an increase in wave number followed by a decrease. Care must be taken to monitor all of these variables so that the spectra can be interpreted correctly.